The video you just saw was a series of plots, and each plot had about 1,000 data points. The goal of the computer program that I wrote was to be able to learn those curves, or to basically fit a curved line to those points and to try to understand a trend. And why do we have to do that? Why is that an important problem? Well, it allows us to then generalize past those 1,000 data points and understand the trend of what we're seeing. In order to understand that in more detail, we have to look at the neural network architecture that enables all of this inside of the topic of machine learning, which is a part of AI, or artificial intelligence. And if we were to dive deeper into that, there's a lot of complexity. So what I thought I would do is to start with a very simple example. Why is it simple? Well, if you can see here, we have got a chart which has far fewer data points. Instead of 1,000, we're looking at 7 data points. And the other thing here is it's not really curvy. It's more linear. Linear meaning it's more resembling a line. You could probably imagine a line that goes right through these points. Now, it won't be perfect because, of course, you do have some, non-linear aspects to this. But that's how the real world is. Nothing is ever really perfect, right? If it's perfect, you probably don't even need to go and do advanced statistics and mathematics and advanced computer science to understand the trend. Instead, you could come up with a very simple equation, right? But in this case, although this is a simple example, it doesn't fit a perfect line, but you can kind of see where a line could be drawn here to understand this data. Now, what is this data? Well, you can make that up, right? Because this is experimental data. We don't know the source of it, but you can think about your own field or your own interests and think about what this might mean. I'm going to provide my own example just to give you an idea of what do we mean by experimental data, right? Now, this could be data that we measured in a lab, or it could be data that we found out in the real world. Since I'm a sports fan, I am going to give a story about how I might have accumulated this data. What I'm going to imagine is that these X values, it's just a simple example that I'm going to try to, explain. And not a perfect example, but just something that I think will get your mind going down the direction of how this data might have been accumulated. So I'm going to say, for example, that I'm a basketball player and I've got a set of basketball games coming up. And what I wanted to do was to measure the number of hours leading up to each game that I practiced. So in the first data point here, I practiced 2 hours. And then the Y is a measurement of how many points I scored in that game. So I scored 3 points in the game that I practiced 2 hours for. And it could be one game or it could be multiple games. Let's say I practiced 2 hours leading up to 3 games, and then I've taken an average. I've scored an average of 3 points, for example, right? However you want this story to go, right? Because we do have 13.5 here, which doesn't look like it's a single data point of points, right? You could say that that's an average, right? So for example, in the games that I practiced 5 hours leading up to those games, I scored an average of 9 points. And in the games that I practiced 11 hours, I was able to score 24 points. And this is something that you might expect, right? The more you practice, the more you score. Just as a general heuristic or rule of thumb. This could be other data, however you might want to imagine that. Now, That's fine. You've got experimental data. You've gone out there and you've done some measurements, you've done some predictions, or sorry, you've done some measurements, and what you want to try to do now is you want to try to predict. But it's hard to predict, right? Because what might a question that you might ask, what a question that you might ask is, what if leading up to the next game, right? I've got a game coming up in a week, and I've only got a certain number of hours. What if I allocated 3 hours to practicing basketball? How many points can I expect to score in that game? Or what if I practice 14 hours, which is off this chart, right? How many points can I expect to score? Does it make sense? Now, off of this chart, you might expect that it doesn't form a linear pattern, but that's fine. Here, it's kind of linear. Now, once you get to here, maybe you're looking at 14 hours, 20 hours, 100 hours. You're not gonna score 100 points, or you're not gonna score 200 points, right? There's a limit to the number of points that you could reasonably score. So it would probably start to taper off. But at least within the window that you're looking at here, you would expect some type of linear pattern. And those are the kind of questions that we would like to answer. We can't measure everything out in the world. We can only measure certain numbers of data points. Everything else you want to be able to predict. And that is essentially what all of machine learning turns into. It turns into looking at data, understanding trends, understanding patterns, summarizing that in a model, and then using that model to be able to make a prediction, and then measuring how good that prediction was and adjusting the model and making the model better. So that's, if I were to describe what machine learning and AI is, that would be it in a nutshell. Now, of course, it gets a lot more complicated than that. We're looking at a very simple example. We're really only looking at one input and one output. You could make this a much more complicated model. You could be looking at other X predictors, right? It could be, how much food did I eat before the game? That might have an impact into how many points I score. How much sleep did I get the night before? There are many other things you might want to measure to make this a lot more better model. But let's start simple, and we'll build up. So when we look at these data points, the next thing is to fit a curve, fit a line or fit a curve to it. I think here we would all agree that it's probably going to be a line that makes the most sense. Now the question is, how do you do that? Well, this is very simple. So you could do what's called linear regression, and there are easy ways to do that mathematically, which involve taking the average here, taking the average here, and that would be the intersection would be where the line would go through, and you do a few more simple mathematical steps, and you have a line. So it's that simple, right? Just use a formula, you can figure it out. But we're not going to do that today, and the reason for that is we're going to do a slightly more complicated set of steps. And although you don't have to do that for this set of data, the point of that is to learn how neural networks work so that we can make it a lot more complicated when we come across far more complicated data. So bear with me. This might seem like we're taking unnecessarily complicated steps, but there's a reason for that. So a line, right? When we talk about fitting a line, the one thing that I think you might have learned when it comes to a line is the equation for a line, which people can write as y equals mx plus b. So let's take a look at that, right? For example, this line right here can be described mathematically or algebraically as y equals mx plus b. What is m and what is b? In math, you probably have heard that the m stands for the slope of the line, how fast it's increasing or decreasing. And the b stands for the y-intercept, which is, if you were to extend this line to the y-axis, where does that hit the y-axis, right? Which point of the which part of this y-axis does this line hit? In this case, it hits the one. The point right here, 1, right? If you extend that, you probably can't see that perfectly well, but that's what this b value gives you. That's what you've learned, and that's totally correct. But in machine learning, it helps to think of this in a different way and use some slightly different terminology. We can think of the b as a bias, which basically means that how much you want to shift this data, right? So right now it's at 1. Now what if I were to change that to something like 5? Now what you would expect is you're going from 2 to 5. So it's going to shift all these data points in this line up. And that's exactly what it did. And you can't really see that. If we were to make it, let's say, it's going to go make the chart look a lot different, but let's just say 50, just to illustrate the point. It went up higher. So you're biasing the data, right? You're biasing that line to shift it up. And if we were to make it negative, you would expect it to go down, right? -5, for example. Boom, it shifts it down. So now that's going through, if you were to extend that line, it would go through -5. You can see how that kind of extends out to beyond 0 and to the negative side of this y-axis. Now, the weight is the slope, right? So it's kind of like the rise over the run, which you've heard, but let's move this back to 1. And what you can do is you can play with this weight to change this slope. So right now, as you move 1 unit on the x-axis, you move up 10 units. So you're going from 20 to 30. Or if you move up 2, you're going up to 40. So you're moving up 20 units. That's because of the weight or the slope of this line. If you want to change this, you can say, let's say, for example, 20. Now that's going to move up even faster, right? So the rise is even faster. But if you want to make it negative, what happens if you make it negative? -5, for example. Now you're going down. The slope is going down, right? Because it's just saying as you move forward 1 unit, you're going down 5. Okay, so simple linear math. It's just essentially probably stuff that you're already familiar with. It's good to review. And you can play with these numbers. The goal of playing with these numbers is to fit a line that seems to match this trend, right? So you can play with it a bit more. And what about 4? That seems closer, but it doesn't seem close enough. You could do better than that, right? So what if you try to make it 1? Looks like we've gone too far, right? So somewhere between 4 and 1, which let's say, this is good, but it's not good enough. So we want to make it, let's say 2. Now that looks really good. It's actually gone through one of these measurements and another measurement, so 2 of these measurements, and it's close enough here, right? That's a really good trend line. So now you could probably predict 3, what 3 would be, and then you could also try to predict what 13 would be. So if you spent 3 hours practicing, how much do you expect to score? If you spent 13, 14 hours practicing, how much would you expect to score? That's the power of this model. But it's a very simple model, right? This is your model, right? So this is your model, and it has 2 degrees of freedom. What does that mean? Well, it essentially has 2 values that you can play with. You can't change anything else. So it's a relatively simple model. It's a very simple model, and you can't really do much with it. But it's enough for this data, right? So it's perfect for this data. Now, I've mentioned in this whole time that we've been talking about this red line that it looks good, it looks bad, it looks really bad, it looks, better, right? So those are all kind of adjectives. But, when it comes to math and computer science, you've got to be quantitative, right? Not just qualitative. You're trying to make quantitative observations and analysis. So you want a way to be able to say how good or bad this is, right? So let's say 10. That looks really bad. It doesn't match this trend at all. But how bad is that? So it would be nice to be able to look at one number that describes how good or bad this line is, right? And that's what we're going to do here, right? So we're going to look at the predicted data. This is what we predict based upon this model. And loss is one number that tells you how bad is my model, right? And the higher this loss is, you can think of it like losing a basketball game, for example, or losing any sport, right, by a certain number of points. You've lost by a lot. Like this is a bad model, right? 25,000. What you're trying to do is you're trying to reduce that. So this is a quantitative way of saying how bad it is, right? And how do you get this loss? Well, what I've done here is I've taken these same data points of input, right? The X values are the same. So I just literally just have a reference to that. And of course, this one is just a reference to that. And then I've calculated the output based upon this model, right? So you can literally see that at the 2, your model is predicting 21. That's the output of this model, right? And how is that? Well, that's, again, y equals mx plus b. So you take the input, multiply it by the weight, 20. So 2 times 10 is 20. And then you add the bias, 21. It's really that simple. Let's take this one. 10 times 10 is 100, plus 1 is 101. So again, 101 is this point right here. Now, the next step is to find the error. How far off were we, right? So the error here, there are different ways of calculating error, but the way that I've used here is one of the more simple ones. It's essentially the difference, right? The difference of these two numbers squared. 21 minus 3 squared, or 3 minus 21 squared. The benefit of squaring it is because what you're essentially doing is that there's two things. You don't, let's say, for example, some of these lines were, so this line was above certain numbers and below certain numbers. Like, let's say, let's go back to a better model here. This is above and this is below. If you don't square it and you just take if you just subtract, then these are going to kind of cancel out. And you don't want them to cancel out. So when you square it, everything's going to be positive. So the error is always going to be positive. The other benefit of squaring it, instead of taking the absolute value, is that you want to penalize it more for being further away. So here, it's very close. So you're going to incur a certain penalty, a certain error of, let's say, for example, this is data point 7. So 2.25 is your penalty. It's a bit off. Here, it's much further off. In this case, you're further off. So you want your errors to grow exponentially. That's another benefit of squaring it. So the further you off, the more penalty you incur. And some of these points are like almost perfect, right? And what happened to our loss? It went down from 25,000 to 13.5. This might be the optimal weight and bias for this model. And but it could be, this is as close as I can get, but the computer could probably get closer, right? I mean, what if I don't even know, but 2.1, would that be better? No, that actually made it slightly worse. What about 1.9? It didn't actually help it much. But what if you play? Okay, so let's put this back to 2. You're just kind of playing with these numbers and seeing what seems to be better. That went the wrong way. So you were looking at that loss as we changed these around. That actually improved it, right? So 0.9 is better than 1, right? So we're improving it. So this is great. This is a step ahead. Why is it a step ahead? Because now what you can essentially do is instead of eyeballing it and just saying, well, that looks better, or that looks worse, you're able to have a number that gives you that feedback. This is how good you are. This is how bad you are. And the goal is clear. The goal is to keep this number as low as possible. Can you get this number to 0? In this case, you can't, because you can't fit a line that perfectly covers every single one of these data points. And you probably don't want to either, right? You don't want to make it a perfect one. Why is that? Well, because there is some experimental error oftentimes that's introduced. There's some noise that's introduced. You don't want to what's called overfit this data to these points. Like, just imagine a curved line that goes through all of these. You don't need to make it that complicated. You just want to have a general rule that allows you to calculate a prediction. Your prediction doesn't have to be perfect, but it has to be as close as you can get it. So this right here has made it a lot easier for us to narrow in on an optimal weight and bias. That's great, but can we make this even better? What I was doing here is I'm starting with 10, right? And then I'm going, I'm using 10-1 as my weight and bias. And I'm just kind of guessing. I'm just saying, well, I kind of feel like this is growing too rapidly, so I want it to kind of slow down. So I'm going to move it down to 5. It's gotten better. That's great. Now, but I can do better than that. So maybe I try 3, right? I'm just kind of playing with these numbers and guessing and checking, right? Guess, check, right? Wouldn't it be better if I could get the computer or this Excel program or a Python program, for example, to instead tell me suggestions on weights that I can do to kind of reduce the loss? Now, think about that for a minute. Instead of me guessing which direction these weights and biases should go, what if I could get Excel or Python or any computer program to tell me the direction to move in, or a suggestion to move these weights and biases in order to reduce the loss? Well, the good thing is mathematics provides us the answer. Now, it's a bit more advanced mathematics. It's not just the multiplication, addition, and subtraction and squaring that we did here, right? You have to use calculus, but that is essentially the power of the technology that we use to do machine learning with neural networks. So it's a bit more of an advanced topic, but I think with this simple example, we can actually work through this. So here, what we're doing is we're calculating suggestions using calculus. So let's forget about the math of this, right? This is the math that we'll get into. But let's take a bigger picture step here. Let's just actually look at what this math helps us do. Now what we have is we have a model with 2 degrees of freedom. We have a calculated loss, which shows how bad is my model. And then we have a suggestion. How do I make my model better? These 3 things, a feedback loop, right? Forget about all of the other numbers. Just look at the power of what we have. We have a model which starts out with some values. We have a loss, which tells us how bad our model is or how good our model is. And then we have a suggestion. That is super powerful. And how powerful is it? Well, let's take a look. So with this simple math and this slightly more complex math, what we arrive at is this suggestion. And it says, what I want you to do next, right, is to change the weight, right? So this is the weight and this is the bias, right? This is the suggestion that this math is telling us. I want you to change this weight to 0.95. So 0.95. So I'm going to change that. And that reduced the loss, right? So the suggestion is to reduce the loss, right? Now you might be thinking that wasn't a great suggestion because we're still off. But the point is that we're reducing the loss. We're making it better. So through iterations of this feedback loop, we're making this model better objectively, right? Not just we think it's better, but it is better because the loss has reduced. Now, that's one loop, right? So now we've got a new value here. I could change the bias as well, but let's focus on the weight for now. And the next suggestion is, in order to reduce the loss further, it's realized, this math has realized that this has gone too far, right? It was too high, now it's too low. So now it's telling me to go back up, bump it back up, 2.138. Let's say, yeah, we'll just call it 2.138, right? So now this is the new suggestion. So I'm going to put that into my model. And now my loss is 21. It has reduced the loss. In 2 steps, right? Starting from 10, we went down to 0.9, improved it, and then improved it further in just 2 steps. And now, I mean, that's a really good model right there. But we could make it probably better, right? So let's just say, now we're just kind of tweaking it because the computer is suggesting that, right? So that the loss went down there. It says 1.99, which is essentially 2, but we'll just even call it 1.985. 13, it's really good. That's really, really good, right? It's kind of narrowing in on, see, these adjustments are getting smaller and smaller. So now it's just kind of tweaking it, and you can tell the computer how many iterations you want to go through. But let's just say 2.006. Now this is something a human can't do. You can't tweak it to that detail, right? But we're using math and computer science in order to be able to do this. Okay, so the loss isn't changing much, right? I mean, it's such simple data that you're not going to be able to milk this for, too much more. But that's good enough. I would be happy here to call this my model. So what is this magic, right? What is this magic is probably the question. How do you actually have the computer to tell you what to change these values to? Well, let's reset these numbers back to where we started. The question at a high level of what we're trying to achieve, right? So our question is going to be, how do we reduce loss by changing these 2 numbers? That's their question at a high level, right? And whenever you talk about change, you introduce calculus, because calculus is the study of numerical changes. And in this case, you can ask yourself, if I change bias, then how does that impact loss, right? Well, how does it impact loss? Well, it's not a direct relationship, because changing bias first changes your output. And then changing your output then changes your error. And then changing your error changes your loss. So it's kind of a steps, right? So instead of saying, how does bias change your loss? Because that's a bit confusing. Let's change bias. Let's move it up by 1. Your loss went up by who knows, right? It's hard to calculate, right? You don't necessarily want to calculate it directly. But what you can ask yourself is, when I move bias up by 1, how does my output change, right? So right now, this is at 21. What if I change this to 2? That went up to 22, 42. They all went up by 1. So that's what this number right here is, 1. A change in bias of 1, increase in 1, changes your output by 1. Okay, so that's pretty simple, right? Essentially, all you're doing is, let's change it by 3. If I change bias from 2 to 5, what would we expect the output to change? Instead of 52, we should expect it to go to 55, because we're increasing it by 3, right? So you change it by 1, it goes up by 1. You change it by 3, it goes up by 3. You change it down by, you reduce it by 5, it should reduce by 5 as well. So let's say we move that down to 0, we should get 50, right? Okay, so this is the study of change. Enter calculus. But that's a simple one, right? How does the output change when you change weight? Now, it's a bit more tricky, but it's not too bad. Not too bad just yet, right? So the output, let's try it out. Now we're at 10. What if we change this to 11? We're changing it up by 1. So let's look at this. This is at 20, right? So if we change it up by 1, what happens to the output? It went up by 2. But that went up by 4. That went up by 9. That went up by 11. So the output is now changing by the value of the input. When you change the weight, the output changes by the value of the input. So that's what we've written down here. As weight changes, output changes by the input. So these two are relatively straightforward, right? The next thing is, as output changes, how does the error change? This is kind of like a chain reaction, right? You change two things here, and everything else below it changes, right? Or in this case, everything else here changes. All of this changes. And now we're trying to figure out how does it change, right? So we figured out this part. As you change weight and bias, how does the output change? Now the next step is, how does the error change when the output changes? Okay. Now for that, we're going to have to use a bit of calculus. Instead of playing around with these numbers, what's easier to do is to look at the equation of how this error was derived. Now, if you recall what I said, what we're doing is we're subtracting and taking the square of that. We're not going to get into the derivatives of functions. Definitely a lot of content out there describing derivatives, but essentially understanding how things change, you can take the derivative of this function, and that would be the change in error as a function of output. So when you have, so you can look up the power rule, and when you have something that's squared, what you do is you bring that 2 exponent to the front and multiply. And that's exactly what we did here, 2 times this. And that's the equation for the change in error as output changes. And now you can see this chain reaction, right? So as this changes, we figured out how this changes. As this changes, we figured out how this changes. Now, the last step is to say, how does this affect this? And how you do that, it's called the chain rule. It's chain reaction. How you do that is it's called the chain. In calculus, it's called the chain rule. You essentially multiply. So weight changes output by the input, and then output changes error by this. So you multiply these two together to get how much weight changes output. And that's what we've done here. Now input, right? This is just to show you that this is input, but instead of in the actual formula, you have to point to the number, which is the input, right? So you're multiplying the output error value here by the input in order to get the effective weight on error. And the same thing with bias. You have to multiply this value and this value to get how bias affects error. So what we have now is the effect of changing weight on error and the effect of changing bias on error. We average that. We get the average of all of these values. And then we have a learning rate. What we don't want to do is, use this straight away to change our weights and biases. We kind of have to temper it down It's called a learning rate, and there's a lot of science around what is the best learning rate for a given problem. In this case, I'm trying 0.01. So all we've done is we've taken this average and we've multiplied it by this learning rate. And so we've got a suggested adjustment, right? And so the adjustment that the computer is calculating for weight is 9.05, and the adjustment that it's calculating for bias is 1.11. Now, what's the goal here? We're trying to reduce loss, right? So what it's saying is, if you were to adjust it up by 9, if you were to adjust this bias by 9, you're going to increase, right? So as you increase this by 9, you're going to increase the loss. But that's not what we're trying to do. We're trying to reduce the loss. So we have to subtract this adjustment from the weight. And that's what the suggestion is, right? So the suggestion is to take this weight that you currently have in your model and subtract out the suggested adjustment. And so that's what you get for your suggested values. So how do I make my model better? Use these values, right? So now you've got 0.95, or let's just say 0.949, right? That's your suggestion. And all of this gets updated as well. So let's go back. Let's look at this intuitively. 10, if you look at this line, it's above, right? So you need to subtract, right? So you need to bring it down. So that's why the value, that's why the adjustment is positive here. You're subtracting out the adjustment. Now, when you make this change, the red line, 0.949, now the red line is below the data points. This is our target, and this is where we are with our model. So now what the adjustment is telling you is that you're too far down. So you need to now subtract a negative number, which means you're increasing your weight. In order to reduce loss, you have to increase your weight. So now the new suggestion is 2.14. Okay, so now it thinks that you're a bit too high. So it's going to try to bring you back down to 1.98. Okay. So we've talked about the math to arrive at this number. We've talked about the math to arrive at this number, or at these two numbers. And of course, I could tweak my bias as well, depending on how critical it is to get it as close as I can to a zero loss, right? But looking at these three boxes, I think the main takeaway is that this is a feedback loop. You kind of go in a loop here, right? You start with a bias, you figure out the loss, you get a suggestion, you use that suggestion, and your loss changes, hopefully for the better. So this loop here is an iteration, right? And you can tell the computer program, how many iterations you want it to go through. What we call that iteration in machine learning, we call it an epoch. So you would have seen in the video at the top, you would have seen which epoch we're going through. Obviously, this simple set of data points, we were able to, quote unquote, learn it in 2 or 3 epochs, depending on how close you want to get to zero. What I want to also do is to bring out, this is very simple because it's just a y equals mx plus b. But how does this relate to neural networks? Well, let's take a look at this picture right here. What we've got here is a very simple neural network. Now, we talked about weights and biases, right? So if we were to draw this in a diagram, what we could do, you probably wouldn't do that for such a simple model, but what you could do is you could have an input. So for example, so you have an input. In this case, you just have one number that's coming in as an input, and your goal is to have one output. How do you get to the output? Well, it goes through this, which you multiply a weight, and then you add a bias, right? So, for example, with the input of 5, let's simplify this model a bit, and let's just say the weight is 2 and the bias is 1. Now, with this input, you've got 5 times 2, which is 10, and then you add the bias, which is 1. So you've got an output of 11. That's it. This is a neural network. This is the neural network picture that describes what we've just done. And it's really that simple. I mean, if you understand this process, that's exactly what the video that I had shown earlier in this series is doing, right? So obviously this is a much simpler example, but we can add complexity to this in order to learn more complicated data. but this is the key here, right? So you specify the number of input layers, in this case 1, the number of output layers, and between these neurons, you always have a weight and you have a bias. So how do you make this more complicated? Well, you don't want to make it more complicated unless the data requires that, right? So let's take a look at a slightly different data, right? So we've got this neural network right here. And what we're going to try to do is we're going to try to fit this simple neural network, or this simple weight, bias, loss, suggested feedback loop, to this data. This data doesn't look linear, right? I've changed the y output, right? So this data is kind of more of like a curve, right? So, but that's fine. We're going to try to see what we can do. The loss, as you can see, is already quite high, 400. So let me just kind of see if I can take this suggestion right here, right? So it's still suggesting me something, 0.868. The loss went down, but not much. So 4.99. I mean, the loss is going down, but as you can see, I mean, let me try to see if I can put like 5 and see what happens. Obviously, the loss is really bad there. What about 0? Yeah, I mean, no matter what you do, I think you can see that you're not going to get a model that reduces the loss significantly enough. So when you have a 0, 2 here as your values, the suggestion is 1.37, and then 1.98, for example. I mean, it's not gonna reduce this loss much. So what does that actually tell you, right? Well, what that tells you is that your data and your model don't match. There's no way that you have enough degrees of freedom by just tweaking these two numbers that you're ever going to get a curve. So what that tells you is that this model right here, which is represented by these numbers, is too simple, right? How do you make this more complicated to be able to, slightly more complicated, right? This is the next step. It's just one curve, right? You could have multiple parabolic shapes instead. But in this case, how do you actually make this slightly more complicated in order to be able to fit this better, in order to have much lower loss, closer to 0? That's what we're going to take a look at in the next video, is how to make this model slightly more complicated in order to fit this type of a curve.